So I'm Shangtong. I was a master student with Rich and just graduate. So today the topic is exploration with the distributional perspective of reinforcement learning. So distributional reinforcement learning has achieved great success in various domains. But the most annoying part of distributional IO is that although in distributional IO we learn a full distribution, but our decision making is still based on the mean of the distribution. So if we just use the mean, why we learn the whole distribution? It seems we are wasting much information. So in this presentation, I will talk about several ideas about making use of the full distribution to improve exploration. So in case you are not familiar with distributional IO, I will start with some basics about distributional IO. So distributional IO learns a distribution over return, not only the mean. For example, let's look at this simple MDP. There is only one state and the reward and one action. And the reward is sampled from a normal distribution. So basically, we want to learn the value of S, say Vs. So in standard reinforcement learning, with the increase of data, our estimation Vs will converge to a scalar 0. This scalar is the expectation of the return, so the expectation of the normal distribution. So we just write down that scalar into the lookup table. So this is our estimation. But in distributional reinforcement learning, we want to learn a distribution. So with the increase of the data, our estimation of Vs will converge to a normal distribution. So we want to write down a normal distribution in our lookup table, but it seems difficult. For an expectation value, it's a scalar. We just write down a scalar, but how can we write down a distribution? So we need some methods to encode a distribution. There are various methods to encode a distribution. For example, we can use categorical approximation or Gaussian mixtures. In this presentation, I will focus on quantiles. A distribution can be approximated by a set of quantiles. So quantiles encode certain rank statistics of a distribution. For example, I guess the median is maybe the most familiar, the most well-known quantile. It's a median is a quantile encode about 0.5 quantile index or quantile level. So see this example. This is the probability density function of a random variable x. And the x-axis is the value, and the y-axis is the probability density. So to encode this distribution, we first divide the area under the curve into, for example, 10 folds. So then each segment is 10% of the total area, and we use the median of each segment to represent this segment. So in general, now we have 10 medians. We use these 10 medians, also known as 10 quantiles, to represent this distribution. So whenever we want to write down a distribution, we can simply write down those 10 scalars. In this way, we are able to write down a distribution rather than draw a PDF.
Shangtong?
Hi.
But if you did that, you wouldn't be able to recover the mean. Because you only have the median of each segment.
Yeah.
So you wouldn't, I don't say you would ever recover the mean. You lost that information.
Well, I guess maybe I'm wrong. Maybe the mean of each segment. Anyway, if you take the mean of all the quantiles, you can get the original mean.
Okay.
So based on this idea, Dabney proposed the quantile regression DQN. So quantile regression DQN maps a state action pair to a value distribution. In this talk, I will treat QR DQN as a black box. I won't talk about how it works, but just assume we have this algorithm. It will take as input a state action pair, say SA, and it will output a distribution. This distribution is encoded by, for example, 10 quantiles. So the input is a state action pair, and the output of this algorithm is 10 quantiles representing a distribution. The distribution of the value of that state action pair. So now let's turn to explore. Basically, we explore because we are uncertainty about the future. there are two kinds of uncertainty in reinforcement learning. The first kind of uncertainty is parametric uncertainty. This uncertainty comes from estimation. So because we want to estimate something, but we don't have enough data, so we are uncertain about our estimation. So with the increase of the data, this uncertainty will finally disappear. So Bayesian methods, for example, Thomas sampling, can be used to capture this kind of uncertainty. There is another kind of uncertainty named intrinsic uncertainty. This uncertainty is from the MDP itself. For example, this reward is not deterministic. It's sampled from a distribution. So this intrinsic uncertainty will not disappear even if we have enough data. It will still exist. So we use the distributional reinforcement method, for example, quantile regression DQN, to capture this uncertainty. Optimism in the face of uncertainty is a basic idea for exploration. So we prefer an action with large uncertainty. If we know an action has large uncertainty, which means we don't know we are not confident about the outcome of that action. So we may want to prefer that action to see what will happen. Based on this idea, there are many algorithms, for example, UCB, upper confidence bound algorithm, and uncertainty Bellman operator, and the UCB with bootstrapped DQN. So I will use UCB in Bandit setting as a simple example. So in traditional Bandit algorithms, we select action AT according to its action value QA. But in UCB, we add an exploration bonus. So the second square root term is the exploration bonus. Basically, this bonus is approximated by counting. So we use count to approximate this parametric uncertainty and use this uncertainty as a bonus to prefer action with large uncertainty. So all those algorithms are based on this idea. Find a method to estimate parametric uncertainty and use this uncertainty as a bonus. But to our best knowledge, no algorithms makes use of the optimism of the intrinsic uncertainty. They just use the parametric uncertainty, and the intrinsic uncertainty is ignored. So in this talk, I will present some ideas about making use of the intrinsic uncertainty. The first option is very simple. We can compose exploration bonus with intrinsic uncertainty. For example, remember in QRDQN, the input is a state action pair, and the output is 10 quantiles. And we then compute the mean of those 10 quantiles, and use that mean value as our estimation of QSA. Similar to UCB, we can add an exploration bonus term by the quantiles. We can use the larger quantiles to compose an exploration bonus. So the second term in the UCB DQN equation will be an exploration bonus corresponding to the intrinsic uncertainty bonus. In contrast, UCB uses parametric uncertainty bonus. But here we consider intrinsic uncertainty bonus.
Excuse me.
Yeah.
Does the intrinsic uncertainty go away if you explore more?
No.
So why should we explore with intrinsic uncertainty?
Yeah, I will talk this later. That's a good question. So because the intrinsic uncertainty doesn't disappear, we add another term before this intrinsic uncertainty to make sure it will disappear.
Can you explain this bonus a bit more? Expression bonus.
This is so assume the 10 quantiles are Q1 to Q10, and we use the sum of Q5, Q6, Q7 to Q10 to compose this exploration bonus. Just
divided by 10.
Because we have 10 quantiles, each quantile should be normalized.
You're adding up 5 of them.
I think it should be 10. Because a quantile should be normalized by the total number of quantiles.
Yeah, 5.
we have 10 quantiles. We only use the 5.
The summation
You're only using it 5 over there.
Anyway, this is just a just a different C. So we evaluate this UCB-DQN in 49 Atari games. We see significant performance boost over the baseline quantile regression DQN. So the second option is to select.
What are those results? Am I supposed to learn something here?
No.
No?
So they
Okay, then I'm good.
are just a cumulative reward improvement of UCB DQN over quantile regression DQN. You can see the largest improvement is 3,000.
Why is one so much better than everything else? Like, why for venture is it just completely?
Yeah, because in venture it's important to explore, like Montezuma Revenge. So the second option is to select an action based on a quantile instead of a mean. So in QRDQN we have 10 quantiles, and we compute the mean of the 10 quantiles and use that mean as a measurement to select action. But why not just select action based on a certain quantile, for example, based on the case quantile? We don't use the mean, we just use a certain quantile. If we use a low quantile, for example, we set k to 1, which means we are using a pessimistic estimation of the Q value. If we use a high quantile, for example, we use Q10 to select action, which means we are using an optimistic estimation of the Q value. But the problem is we don't know which K to use. Let's first look at a simple MDP. In this Markov chain, there are n states, and there are only 2 actions, left or up. If you go up, the episode ends with reward 0. If you go left, then the environment will lead the agent to the next state, and a reward is sampled from a Gaussian distribution. If the agent reaches the goal state, the episode will end with a reward plus 10. At each episode, the agent is placed at the first state, and there is no discounting. So it's clear that the optimal policy is always move left. But let's first consider tabular Q-learning with epsilon greedy. We will find tabular Q-learning is difficult to explore this chain well. The reason is to find the optimal policy, we have to reach the state G first. So before reaching the state G, the Q estimation in Q-learning for the action up and for the action left is both are 0. So basically, Q-learning can't distinguish which action is good or which action is bad before reaching the state G. This is because Q-learning didn't capture all the information, so it can't distinguish the 2 actions. But if we consider distributional RL, if we use quantile regression DQN, then before reaching the state G, we can find the value estimation of the action up is still 0, but the value estimation of the action left is now a Gaussian distribution with a mean 0 and a variance sigma. So note a high quantile of this Gaussian distribution is greater than 0. Yeah?
If you had those normal distribution rewards on actions to upward actions and 0 rewards.
Yeah, that's next example. So here we can find a high quantile of this normal distribution is larger than 0. So if we select action based on a high quantile of the learned value distribution, we can easily find the optimal solution. So we benchmarked steps for algorithms to find the optimal policy in that chain. The x-axis is the length of the chain, and the y-axis is the steps that each algorithm needs to find the optimal policy. So we consider 4 algorithms. The first algorithm is naive Q-learning with epsilon greedy. And the second algorithm is pessimistic quantile regression DQN, which means the behavior policy is always derived from a low quantile of the distribution. And the third algorithm is optimistic quantile regression DQN, which means the behavior policy is always derived from a high quantile and the original quantile regression DQN. Yeah.
Do you use epsilon greedy with these DQN?
Yes. So Q-learning is epsilon greedy with the Q value, and pessimistic quantile regression DQN is epsilon greedy with respect to a low quantile, and the quantile QR is epsilon greedy policy with respect to the mean of the value distribution. So we can find with the increase of the chain length, all an optimistic quantile regression scale well. But this chain is human designed to show the benefits of optimistic QR. We also designed another chain. We slightly changed how the reward is given. So now if we go up, the reward will be sampled from a normal distribution, and if we go left, the reward is minus 0.1. And if we reach the goal state, there is a large reward plus 10. So if n is not so big, the optimum policy is still moving left. So we also benchmark the steps for our algorithm to find the optimum policy in this chain. Now we can find the result are reverse. So pessimistic quantile regression performs the best, and the optimistic quantile regression performs the worst. So based on the two chains, we can find that different tasks need different quantiles. Yeah.
Why is there a difference between DQN and QR DQN?
What do you mean by DQN?
The blue and the red.
Blue is Q-learning. Oh, blue is.
Sorry, not DQN, I meant Q-learning.
Yeah. So, and by the way, although I use the word DQN, all the algorithms are implemented with tabular representation. I just use the word for simplicity. So Q-learning, you just learn a Q value. But quantile regression DQN, you learn a distribution. Like you learn several quantiles, not just the mean. Yeah.
So if you're using tabular DQN, are you using also like all the other things like experience replay and?
No,
Oh,
just
so
a pure tabular.
So it's just like, okay.
All the stuff are tabular. No target network, no experience replay. Yeah.
So the mean, like, is that the mean of the red and the blue? They're not the same?
Yeah, they are the same. So there has been a rumor that distributional IRL performs than naive IRL because of distributional IRL provides auxiliary tasks. But we don't know the exact reason that distributional IRL is performed better than traditional IRL. That is, the auxiliary effect is a possible hypothesis.
But in tabular, we shouldn't see any auxiliary effect.
Yes.
Why is it?
Well, Q-learning is winning here?
No, it's not winning. The winner is pessimistic Q-learning.
But don't you want to be low?
Yeah, here we want to use the low quantile. Yeah.
So blue is better than red.
No, the lower the better. Oh yeah, blue is better than red. That's right. So here traditional Q-learning defeats quantile regression Q-learning. Yes.
So in this tabular setting, is there any reason for Q-learning and quantile regression to be measurably different? Like if you get enough runs, is there any reason for them to give you different results?
Yes, because in quantile regression Q-learning, even in tabular case, you need to learn. So in my experiments, I use 3 quantiles to approximate the distribution, which means you need to learn 3 quantity. But in Q-learning, you only need to learn 1 quantity. So the learning speed may be slower. Yes?
How do you decide which action to take given the quantile information?
Select, just use that quantile as the mean. So, and
Quantile.
So for example, we use the first quantile Q1. Then we compare Q1 of SA1 and SA2. If the Q1 of SA2 is larger, then we choose A2.
Are you weighting the means of every quantile uniformly?
Sorry?
Are you weighting the means of every quantile uniformly when? Yeah, right, because you're just dividing over 10.
Yes.
So should any quantile be weighted by the probability of that quantile?
No, the 0.1 is the exact weight for that quantile to recover the distribution. Do you have a question, Matt?
I will in a second. I'm still thinking about it.
I'm running out of time. So basically, I think we need different tasks need different quantiles. So even within one task, we may still need different quantiles in different stages during learning. So we propose to use a hierarchy. So at each time step, first we select which quantile to use. Then second, we select action based on that quantile. So we find that this hierarchy can be formulated in the option framework. So we just use, so this here is some basics of option framework. Due to time limit, I will skip them. And we formulate this hierarchy in the option framework. We name this quantile option architecture. So basically, we use each quantile as an option, and we learn which quantile to use via intra-option Q-learning. Particularly, in the option framework, we have a termination function beta. It determines when to terminate option. In our framework, we consider a constant termination function. So beta in our work is just a scalar, it's a number. It determines how long we commit to one action. No, how long we commit to an option. So this beta can be learned by the option critic framework, and we leave this for future work. So we find that this beta is important. We don't know, there is no universal rule to set a beta for all the tasks. But at least for those two chains, we set beta to 1, which means, we set beta to 0, which means an option will last for the whole episode. And we benchmarked the quota algorithms. We can find the quota consistently achieved good performance in both chains. But those two chains are still human designed to demonstrate the benefit of our algorithm. So we also evaluate the algorithms in 49 Atari games. So we find that there is still, we can still get performance improvement. And we also evaluate quota in Roboschool tasks, which is a continuous action domain. We find the quota significantly out from the baseline algorithms. So related work. So the work in this talk is related to Bayesian RL. It's also related to risk-sensitive reinforcement learning, especially the implicit quantile networks, if you know. We can find something like utility function risk-sensitive policies in our work. Take-home message. Optimism in the face of uncertainty is an important idea for exploration. Now I want to extend it to pessimism and optimism in the face of intrinsic uncertainty. So now I think I can answer that question. So maybe Atari games are similar to the first chain. So we use so a large quantile can help exploration, but that's not guaranteed. Maybe just because some property of Atari games is similar to the first chain, so we can use high quantiles to help exploration. Acknowledgement. I thank my collaborator Boislav Hengshuai, Linglong Bo. This work is done during an internship at RLAD level, Huawei. Thanks.
I have an option. I
So basically each quantile is an option. So the first option is to use the 0.1 quantile for action selection, and the second option is to use the 0.2 quantile for action selection. So we use each quantile as action, not as option.
How do you learn the queues? Where do you, like,
You mean to select a quantile?
yeah.
By intra-option Q-learning.
Yeah, thank you.
Yeah, Nico.
So in the beginning of the presentation, you were talking about a bonus, a reward bonus, and then later on, I kind of missed how that reward bonus relates to the QR algorithm that you were showing results for.
No,
So this is UCB and
Yeah.
QR is a separate algorithm.
So quantile regression doesn't contain any special exploration techniques.
I see. Okay. Thank you.
Yeah.
Is there any reason for having a normal distribution over the quantile?
Sorry?
I think you said in the beginning that you model the action values as a normal distribution.
No. I just use this normal distribution to illustrate the idea of a quantile. But the quantile approximation can be used to model any distribution. Hi. Yeah, Rich.
So this has been very interesting. You did lots of things, but I'm still confused by the first step. Like, how you find these quantiles? It seems to me it's like impossible.
It's because of beta.
It seems impossible because if you don't have the actual points and you're adding points, that you cannot, in an incremental way, maintain the quantile.
Oh, you mean how quantile regression DQN find those quantiles? Do you mean that? There is a
With a tilted L1 loss, you can learn different quantiles. So if you have an L1 loss, it learns the median. If you tilted it somehow, so it's like just rotating the plot by some degrees. Then it learns lower quantiles and higher quantiles, depending on how much that like plot of the L1 loss is rotating.
so quantile regression DQN doesn't use L1 loss.
Yeah,
It uses Huber loss.
oh, it might be that version to be maybe more loss or something.
No,
Different.
if you use L1 loss, I think you should use categorical approximation rather than quantile approximation.
Let's be specific. Isn't it impossible to estimate the median incrementally? You're not storing the individual points. You're only keeping one number. You don't really know where the individual points were, and if you make a small step, arbitrary numbers that you may cross from one side to the other. This seems impossible.
Basically, you can get the sample from the next distribution. You can use that. You can use the sample from the QS. You can use the sample from QS prime to estimate the median of QS prime.
Even if you're given the whole returns incrementally, there's no way you can estimate the median.
You mean the whole return?
I give you a bunch of numbers.
Yeah.
There's no way you can tell me what the median of them was. Maintain it in an incremental way. That's what I'm thinking.
Yeah, you can't do it in.
Maybe you know what the median, half of them are above and half of them below at some time. I'm going to give you a new one. It could be higher, it could be high or low. And how do you incorporate the new number?
You just
Because you want after.
you can use the Huber loss to. You can minimize the Huber loss, but I'm not sure it's incremental or not.
If all you have is the median, how can you maintain one number plus the old median? There's no way to compute the new median. That's what I'm thinking. So I lost you right at the very beginning here. I know this wasn't your part, quantile regression, but as explained here, and I've never seen a good explanation of it.
Maybe it's not incremental, but it's still doable.
Well, more likely, it's not doable. I mean, there's no way you're going to apply this to any application and not have dynamic modulators, like Atari. It's funny. You actually have, you've been running these experiments, right?
Yeah, so
So you take someone's code that
I
does this.
wrote the code.
You wrote the code.
Yeah.
So you know it's impossible.
No, it's. I don't think it's impossible.
Find the quantiles.
Yeah, there is a quantile.
All you have is the median of the quantile, the centers of any statistic on the quantiles, but not the actual data points. If you have the actual data points saved, you can always compute the median. But if you're just saving summary statistic,
We have some sampled from the true distribution, so we can use those samples to estimate the median.
if you have all the samples, you can compute the median.
Yes.
If you've thrown away the samples,
Why should I throw away those samples?
because you always throw away the samples.
So
Because you have, millions and millions of samples.
no, I mean, so at the current state.
Function approximations.
At the current state, we are in state S, and we get state st plus 1. So we get a new sample of st plus 1. We can use that sample to estimate the median.
Anyway, that's very interesting. Good. Any other questions? Yes.
Yeah.
Why is this a good idea? Like, so it makes sense when you have uncertainty over your parameters. You want to gather more information to be certain.
Yeah.
But let's say there's uncertainty in what return you'd be getting.
So sometimes.
The choice would be to just not go with where there's uncertainty in return.
No, sometimes life is hard, very hard. So you want to be optimistic of the life, or you want to try more dangerous things. Yeah.
So the first chain had some stochastic rewards, and those stochastic rewards are followed by big rewards.
Yes.
Some deterministic rewards that weren't followed by a big reward.
Yeah.
And in that case, that optimism worked well. So I think, like in real life, or for example in Atari games, this situation happens often, right? That stochastic rewards are more likely to be followed by a big reward at the end, because that's what the first chain looked like. And that's where that optimistic model works better. Okay. So you have this stochastic reward.
Yes. But I don't know Atari games has similar reward or not. Yeah.
So again, the question is why intrinsic uncertainty should be used to explore.
For example, if you know you won't graduate for your master degree, but you still want to be optimistic about the future. That's the reason why. So if you are being optimistic, you may find something good and you can graduate.
Last question, Matt.
Oh, right. So do you ever run any experiments like just doing optimistic QR in Atari? So,
What do you mean by optimistic QR?
so you had your pessimistic and optimistic. So
Yeah.
either only following the high quantile or only following
No.
the low quantile.
No.
And you didn't run it in
Yeah, I
Atari?
didn't have that experiment.
Okay. Because going with what Hassan was saying, like Atari seems more like this chain
Yeah.
than it does the other chain. I would be interested to see like, would it just do better following some optimistic
The
quantile?
first idea is optimistic, right? Horace's idea.
Yes. Yeah, but he didn't use pessimistic.
How
Yeah.
does it compare against using epistemic uncertainty to explore? Have you done some comparison?
So you want to compare.
It's a bootstrap DQ, and I think it uses epistemic uncertainty.
Yeah, you want to compare parametric uncertainty and intrinsic uncertainty, right? I think it's unnecessary because those two ideas are orthogonal. They can be easily combined together.
How are they orthogonal?
So you can use basic methods for each quantile estimation. In this way, you can have both. You know both.
I thought Matt was the last question. Yeah, I'm sure it was the last question. Well, thank you very much.